key points up here, the particle in the box. And I kind of want to move to a different system today. In the end of this class, the goal of this class is to be able to come up with a rigorous way to define chemistry, to calculate anything in chemistry we want from the first principles or from the ground up. And so we could sit in the particle in the box for another week, but we're going to start losing sight of that goal. Because the periodic table, the particle in the box model really only gets us, in fact, it only gets us a third of the way effectively. And I'll explain what I mean by that. And so what I want to start today is basically our journey towards the hydrogen atom. We don't quite have all the math for the hydrogen atom and all the ideas we need for it. But we should start that math. We should start that theory. Start thinking about what do we need to learn, what tools do we need to solve the problem of the hydrogen atom. And then we'll be able to conquer that in a couple weeks. Hydrogen atom is actually not too difficult, but we just need a little bit of couple concepts to get there. And then we'll move to molecules, right? We'll start learning to put hydrogen atoms together to make molecules. And that will require a different set of tools as well, but they all kind of build off of each other. So typically in PChem 2, when you teach this class, after you particle in a box, we usually jump into what's called the harmonic oscillator, which is our model for bonds. And the way that we've structured this class is we're kind of building up towards chemical molecules. So I think it's really appropriate to start with the harmonic oscillator, or the model of a bond, because we're going to not use it for a while. Because then we'll have to go back to the hydrogen atom where it's not all that useful. And so we'll do the harmonic oscillator later. Instead, we'll just start with the idea of an electron orbiting a nucleus. So before I do that, I want to talk about the kinds of energies and the kinds of things we're looking at. And the fact of the matter is that the particle in the box model is just a model for translational motion in some direction for a particle, right? So we have different types of motion, and we're going to study. And what we'll find is that for chemistry, there's 3 kinds. There's maybe 4. We'll say 4. And we'll tackle models that allow us to represent each one of them. And what we'll learn also is that these are all separable. We can talk about one type of motion and not the other. They don't always communicate with each other, and they don't work. You'll understand what I mean by that when we start thinking about them a little more. But we can kind of tackle them separately. And so if we think about having a molecule or an atom, let's just think about a molecule for a second. Consider a molecule. Let's just do one of my favorites. Acetonitrile. Okay, CH3CN. What kind of motion does this molecule have? Well, there's a very simple one. The first one, we've already kind of studied it. If we put this molecule in a box, we can study its translational motion through the box. Right? This idea of translational motion. This is X, Y, Z motion, if you will, right? You're just moving the molecule through space. Right? We can use the particle in the box approximation for this, right? We can define our box as our space that the molecule's in. We can calculate its translational energy levels, right? How much energy it has as it moves through the box, left and right through the space, right? And we can just use the particle in the box approximation here. All right, so we've already actually calculated. We've already defined the theory for translation, right? This idea, we've only defined it on a line, one dimension, but turns out you can make a 3D particle in a box, right? Just make it a cube, and you end up getting the same math. It's just in 3 dimensions instead of 1. They actually just add up together. It's not any more complicated. You just have 3 numbers, indices for each axis instead of just 1, and m and some other number. But so we know this idea of translation, right? We've already solved that. But there's other ways this molecule can move that don't involve translation. One is that we're going to learn about, we're going to study this one a lot, is vibrational motion right, which is the motion, is the stretching of bonds, right? Inner kind of the atomic coordinates of the atoms moving with respect to each other, right? So there's this idea of say, a stretch, right, where the C and the N pull apart, right? You can stretch your bonds, right? Doesn't matter what kind of bonds. We can bend these in, scissor motion, right? You know and love these motions from organic chemistry. Right, but that's another type of motion, right? The molecule can stay in place, and we can adjust its energy by stretching its bonds, right? The molecule hasn't translated at all; it stayed in the same center spot in our box, but we have changed the energy of the molecule by moving its atoms, right? So this is motion of intra-molecular coordinates, or translation of atoms in a molecule. Okay, so we can move the atom, we can move the coordinates separately, and the way that we're going to study that is through this harmonic oscillator approximation. We're going to treat our bonds as springs, right? So I'm going to write harmonic oscillator, but what I really mean is the spring approximation. All right, we're going to treat the bonds as springs, and we're going to look at how the energies of the system changes as we stretch or compress the springs. Right, so that's a different type of motion completely from translation. There's one more, there's actually two more, but we'll focus on one because it's be really relevant for our discussion today. And so you can also do another type of motion in a molecule without moving it or translating it, which is to rotate the whole thing. Right, we can spin this molecule with some angular momentum. Right, so we call that rotational motion. Which is imparting a molecule or some system with angular momentum to spin on its axis. And that's another form of motion as well that will change the energy. The more that we want to spin our molecule, make it spin faster and faster, the more energy we have to put into it. Right? So you're going to raise the energy of the system by rotating it. And there's one final type of motion that we'll analyze. It's similar to particle in a box, but instead we're looking at the molecule itself, which is electronic motion, which is the motion of electrons contained inside molecules, or inside bonds or molecules. All right, in some way, we already looked at this with the butadiene example last class. The idea that we treated our molecule as a box, and we looked at the motion of the electron through the box. But if you imagine that like that motion happening, that electron moving through the box, or through the molecule like a particle in a box, that motion doesn't actually impart any force to the molecule. The molecule can still stay fixed into the center of the box, not moving, while these electrons are oscillating back and forth through the molecule. Okay? So we'll talk about all four of these. Well, we've already talked about one. We talked about translation, right? That's just particle in the box. Right? We haven't talked about vibration. We'll get there later. And so we have these last two that we have to deal with. Electronic, we haven't even defined what a molecule is yet, so we can't really talk about this, but we have an implicit sense that electrons can move within molecules, in between nuclei, if you will, as the electrons are shared in the bonds between the atoms. So we're left with this idea of rotation, right? It's something that we can think about. And it turns out that thinking about rotation is a really good idea for tackling the simplest problems in chemistry, because the simplest problem in chemistry is the angular momentum, or the rotation of an electron around a proton, which is just a hydrogen atom, right? All a hydrogen atom is a proton centered at the center of their atom, and somewhere way out in distance, there's an electron that orbits that proton. And that electron is going to have some angular momentum, it's going to have some rotational energy if it's excited. Right? And so if we can understand how rotational motion or angular momentum works with our microscopic systems, well, then we can understand the exact behavior of an electron around a proton. Right? We can think about these orbits, as you might imagine. Okay, and so tackling this, we're going to generalize it to this idea of angular momentum, because there are going to be what we're going to learn is that there are lots of things in science and physics or chemistry that spin. Spinning things are very common. And they spin in ways that you wouldn't expect them to spin as well. Right? The idea that if you think about a spinning top, like a top that you spin on the ground, like a little toy, right? You can treat molecules work and in terms of electrons as well. They work like spinning tops. That's all they are. They're just spinning tops. So understanding how rotation and angular momentum works allows us to unlock a lot of. It's going to be a really powerful tool for understanding chemistry, because everything's built around this very basic concept. Right? All of chemistry is defined by this. Right? It's the idea of an electron in an orbit around a proton. What does that look like? Right? What are the physics of that? Right? And that's going to be our solution. We're going to have to, in order to figure out how this works, how the electron arranges its energy levels around a proton, will be involved with understanding the angular momentum of it. Right? So there's going to be some angular momentum, some angular frequency, right? We have some angular frequency. There's some distance r, right? And the angular momentum of our system, if we look at it from physics 1, angular momentum is written as L. And we have some momentum, linear momentum in this direction. Right? So you have some momentum of your electron going around an orbit, distance r around your proton. The angular momentum is the distance, the radius across the momentum. Okay, so we understand these two concepts already, right? The idea that we have a distance, right? We've calculated observables relating to distance. We've talked about momentum. We know what that looks like, right? And all angular momentum is, which is where you're applying a force or momentum. You're applying some force perpendicular to the line between the center point and your orbiting electron. When you apply a momentum like this in a stable orbit, then you generate some angular momentum. Okay? And so we can do this in physics, right? We can look at this as like a ball and a chain or something like that, you know. And so we're going to have to do those same physics, but for a proton and an electron. And what we'll find is that the physics of this and the behavior of an electron around a proton is very different than a classical system. Very, very different. Okay, so using our insights about things that spin, you know, figure skaters spinning around their arms and stuff like that, some of those things will make a lot of sense to you and will make sense here, but there's going to be a lot of things that break down in that idea, that the electron and the proton orbit themselves like the sun and the earth, if you will. Right? If we treat this system as a sun and an earth, you get the wrong answer. Right? So we know it breaks down somewhere. And I want to talk a little bit about that story today to motivate our discussion about how to treat angular momentum properly. Right? Once we understand that, then it's going to be no problem to figure out the hydrogen atom. Right? We just have to, once we understand how the electron, how it works, how the electron orbits the proton, and we can define the physics of it, then we can define the Schrodinger equation for the hydrogen atom and solve it. Right? And so that'll take us a little bit of time. But these tools that come out of angular momentum are very powerful, and we'll be able to apply to a lot of different situations. One thing that I want to write, just kind of mention, just off the top of our head, we'll come back to this during spectroscopy, but let me rewrite these motions real quick. So we have translational, rotational, vibrational, and electronic motion. And the question we should ask ourselves is, we know that in quantum mechanics that motion or energy is quantized. So there's specific energy levels associated with different types of energy. We saw the translational energy, right? That the energy is proportional to n squared over L squared, where L squared is the length of the box. Right? And what we'll find is that vibrational, electronic, and rotational also have these kind of rules. Right? That energy is quantized by a number and it's scaled by some parameter of the system. right? So translation's dependent on the size of the box. We'll find that rotations, the energy levels are spaced by how big the moment of inertia of the molecule is, basically how big and large the system is, the size of the system. Vibration is the stiffness of the bond. That determines the energy level spacing. And electronic is complicated. But we know that the electronic structure of many molecules looks like a particle in a box. So in some ways we go from all the way back to here. Right? So we'll have to think about that a little bit. But what we can do is think very kind of holistically about where these fall in terms of energy. And if you think of, you make your box the size of an experimental apparatus, so let's say on the order of volume on the order of a meter cubed, right? Maybe we put a molecule, we want to study it in the vacuum, in the gas phase, so we're going to put it in a volume of a meter cubed. Well, that's really big, and the spacings between individual translational levels and these big systems are basically zero. So we don't even have to worry about translational motion for our system. What this means is that in large boxes, molecules and atoms move like particles. The idea is that when a molecule is in a small box, I'll compare with a large box. So in a small box, the energy spacings are large. Right? There's a lot of gap between the allowed energy levels, but in a small box, they all just cram together, like this. Right? So there are hundreds of levels in a large macroscopic box where you would otherwise only have 2 levels in a small box. So this is a continuum of states. Right? So basically, in a large box, a molecule can translate to any energy at once because you can't really tell the difference between the energy spacings. They're really small at the scale of your system. So often we don't even treat molecules translationally with energy levels because the energy level spacing is tiny, which really simplifies our work. Right? This is why the ideal gas law works. Right? The ideal gas law, eventually that's what you ultimately get to. The ideal gas law is that the particles move in this box randomly and they can move at any energy they want. That's just implying that there's hundreds and thousands and millions of energy levels that they can choose from. Right? Not just 2. Right? If the ideal gas law wouldn't work if we assumed that the ideal gas had energy levels like this. If it were like this, the ideal gas law would break down. It wouldn't work at all. So we've already seen this result, and the math that comes out of it is just the ideal gas law. Okay, so we can still use that rule, which is nice, at least practically. Rotations turn out to be, so basically translational energy is like meaningless, effectively, right? Everything is moving. And you can measure temperature. Rotational is a little different. So the energy level spacings between rotational levels, so we'll call that delta E. And if we divide it by h, we get the frequency of the light that's associated with by Planck's law. And for this frequency tends to be somewhere on the order of 10 to the 6 to 10 to the 9 hertz, which means a wavelength of anywhere between 1 meter and 1 millimeter. Okay, so what we're going to learn actually is that if we want to study molecules and how they rotate, we're going to want to shine light at their energy level spacings, which is somewhere on the order of a wavelength of about a centimeter or about a gigahertz. So just as a reminder, this is 1 megahertz to 1 gigahertz. All right, so I'm gonna change between units a lot for energy, right? We can talk about energy in any unit we want in quantum mechanics because E equals h nu. So we can talk about energy in terms of joules, but if we divide by h, we can talk about it in terms of frequency. And if we divide if we divide the speed of light by frequency, we get the wavelength, right? So these are all energy units, and we can use any of them. Right? So and often we'll change as we go through the class. We'll change what energy units we use because some are more convenient than others. Vibrational energy turns out to be, well, if you've ever done it, if you've done IR spectroscopy in organic chemistry, or you will do it this semester, we do use infrared. Right, so the frequencies of infrared tend to be somewhere on the order of 10 to the 9 to 10 to the 12 hertz, and the wavelengths tend to be on the order of 0.1 millimeters to 1 micron or so. Right, so we're going up in energy, if you will. Right? So in fact, energy is increasing. So if we were to study a molecule translationally, we basically don't have to give it any energy to measure its spacings, because the spacings are basically zero. Basically, if you give the molecule any energy, it'll move. But if we want to talk about rotations, what we're going to find is that in order to study rotations, we're going to have to go around at the spacing of the energy levels, which is on the order of about a gigahertz, or a wavelength of about a centimeter length. We call that, of course, these are called microwaves. Right? You typically use microwaves to study rotations, and that's what I do for a living. Vibrations, you use infrared. This is infrared radiation, IR radiation. Right? So typically you use lasers and infrared light sources to study vibrations. And then we're left with electronic. Electronic is much faster. It turns out that electrons move very, very quickly inside of molecules. In fact, compared to the nuclei, the electrons, effectively, the electrons are like flies on an elephant. The nuclei are fat elephants that don't move, and the electrons are just constantly buzzing around. The electrons don't affect the nuclei at all, just like the flies don't affect the elephant. So electronic motion tends to be quantized at much higher energy scales. So the frequencies tend to be on the order of anywhere from 10 to the 13 to 10 to the 18 hertz, which is a wavelength of anywhere between 1 micron and a nanometer or so. Nanometer. And so this is motion of exciting motions of electrons, right? This is visible in UV light. This is why spectroscopy is so powerful, is that what we've defined here is 4 possible ways that a molecule can exhibit energy changes. You can move it, you can rotate it, you can vibrate it, or you can excite its electrons. And depending on what kind of physics we want to probe, or the kind of chemistry we want to think about, or the dynamics of our chemistry, we can choose a range of energy levels, of light, a range of frequencies, a range of wavelengths that allow us to probe those dynamics directly. Right? So if we look at a molecule, just microwaves, we're just going to see rotations. That's all that molecules do. If we do infrared, we're going to see mostly just vibrations. And if we do electronic, we're mostly just going to see the electrons get excited inside the molecules. And so let me just scale these. These are, of course, an increasing energy. But what we're also going to find is that they build off of each other this way. So, for instance, rotations, you vary in a rotational spectroscopy or rotational motion. When you study rotations, you very rarely see electronic or vibrational effects. They're basically you're at such low energies that the vibrations and the electronic motions aren't happening. But as you get the vibrational energies, you're going to start seeing, well, you have enough energy to also make rotational changes too. So as you go to higher energy, the spectroscopy becomes more complex because now you have energy to excite all of the modes. So in fact, complexity also increases this way as well. So if you do an electronic spectrum of a molecule, you're not only going to excite the electrons, but you're also going to excite the vibrations and the rotations. And the same thing for vibration. If you excite the vibrations, you're also going to excite rotations. And then in rotation, all you're going to do is rotate. Right? So the complexity of the spectroscopy increases as well with energy because of this. All right, we'll look at this more carefully when we talk about spectroscopy. Right? This kind of idea will be borne out directly from the math in the theory. But the idea is that we have a tier system, if you will, or a hierarchy of energies or motions in our systems in quantum mechanics. The lowest, which is basically basically classical. There's no continuum. There's a continuum limit for translation in a large box or high temperature. Rotations are pretty much by themselves. Vibrations are more complicated, and electronic has effects from all of them. Right? And there's beautiful studies of molecules from, that have been studied for decades, where they do electronic spectroscopy and they have some idea of how a molecule absorbs radiation and transfers that energy. And when you shine a UV light at it, and what happens is that sometimes those behaviors get modulated because there are vibrational and rotational effects that affect it as well. Right? You have three motions you have to deal with, and sometimes they can combine in strange ways, and you get lots of cool effects. And this, in fact, this idea that a vibrational motion can affect electronic motion, and vice versa, is the entire reason why chlorophyll can photosynthesize light. The electronic effect of absorbing a UV photon to drive the photosystem in chlorophyll, the energy transfer in the electron chain in the chlorophyll system, the photosystem 1 and 2, as they're called, the proteins on the chlorophylls, on the membranes of the cell, they transfer electronic motion by moving things vibrationally. They transfer that energy through bonds, vibrations. And if we didn't have that coupling, as it's called, you wouldn't have photosynthesis, or it would look very different. Right? So in very, very important biochemical pathways are due to the fact that these motions are complex as you get to higher energy. And they affect each other in really unique ways sometimes. And often the most interesting things in chemistry are caused by that. Right? So even though we're talking about things at the fundamental level here, they have extremely important consequences for chemistry. And I hope to illustrate those as we go through this. Okay. So I want to stop now with this idea of hierarchy, and we're just going to kind of go up this level, right? We'll come back to vibrations because we'll talk about molecules later, but I want to stick on this rotation concept. Because again, we're talking about a proton and electron orbiting each other. When in the early 20th century, you kind of have to put yourself in the shoes of a physicist or a chemist at the time. Ernest Rutherford, at the time that this stuff was being developed, all Ernest Rutherford had discovered was that while electrons had been discovered already, but that atoms are basically, there's a proton or some heavy positively charged nucleus, and there's negatively charged stuff on the outside, and there's a huge space in the middle. Right? That's basically all they understood, is that there are these electrons that probably are orbiting these nuclei. Right? If you think about it as two bodies, then the only thing that they can do is orbit. Right? You just think about planets. That's the intuition that they had. And there's a huge gap between them. So if the electrons are bound electrostatically to the proton with a huge distance between them, and the distance is massive, in fact in hydrogen, if the proton were let me think about it. If proton were a soccer ball, size of a soccer ball, and the electron were the size of a golf ball, the distance between them on average is on the order of a couple of football fields. Right? So big gap between the two. And so they understood that this gap exists, and they understood that the electrons and protons coexist simultaneously. And the only way that they could do that in their head was that there must be orbits, right? That the electron is orbiting the proton, right? Like a planet in a moon. And that's the only kind of intuition they had about the hydrogen atom. And so they tackled. So Niels Bohr, the great early quantum mechanicists, said, let's see if we can describe the hydrogen atom with that assumption. Right? What if we treat the hydrogen atom as a planet-moon system, or some stable orbit? But here's a problem, though. There's something that physicists also knew at this time, and you can do this with a normal electron. When you have an electron spin, when you impart an electron some oscillatory behavior, all electrons do is emit light. They emit energy. So if you attach an electron to a positive charge and you spin it with an electric field or a magnetic field, the electron emits light. And so the problem was that they had was, well, let's imagine that that's happening here, right? You have an orbit, a stable orbit of an electron around a proton, the electron is orbiting like this, and what electromagnetism will tell you is that an electron is releasing light, is releasing photons as it does that. And it releases it at the frequency of the orbit. So the faster this electron orbits the proton, the higher the frequency of the light, or the shorter wavelength of light it emits. But the problem with that is that, well, conservation of energy. So this thing's orbiting around here and constantly emitting light, which means this electron is losing energy as light. Right? So the idea was, well, if the system is losing energy as it rotates around, that means the electron is going to have to slow down, and eventually it's just going to spiral inwards. Right? That's what classical theory predicts. That this emits light, and then what happens is it just, as the kinetic energy of the electron slows down, it can't overcome the force of the positive and negative charges being attracted to it, the electrostatic attraction. And so that's going to win out eventually. So eventually there's not enough kinetic energy to compensate for the attraction between the two particles, and the electron will just fall into the proton. Right? So if you use this idea of this being a system like a planet and a moon, but instead of gravity, you have electrostatics attracting the two bodies, then atoms wouldn't exist at all. Right? But the problem is that, yeah, so electrostatics, instead of gravity, implies no atoms at all, no stable atoms at all. In fact, they predict that if you have instead of a gravitational orbit, electrostatic orbit between the electron and the proton, that the hydrogen atom would exist for approximately like 20 picoseconds. It's a very fast rate. Right, it's just going to go whoop into the proton and everything gets destroyed. There's no atoms left. Obviously, that's not true. Right? We know hydrogen atoms are stable, and the electron is happy to orbit that proton for as long as it wants. It'll just keep orbiting. Obviously, it's not spinning in, so there has to be something wrong with that theory. So Bohr comes up with a really clever idea. He says, let's cut half and half. So let's assume some things that are classical about orbits, and then also assume that the energy is quantized, just like Planck did with light. Right? He says, let's assume that you can only release integer amounts of angular momentum. Right? You can have 1 unit of angular momentum, 2 units of angular momentum, 3 units, and nothing in between. Right? Just how Planck said for a black body, the thing can only emit 1 photon or 2 photons or 3 photons. It can't emit 3.5 or 2.21. Right? And so that's the same idea Bohr had. So Bohr's observations are these. One is that electrons exist in stable orbits. At discrete fixed distances about the nucleus. Right? So again, the idea is that I'll just draw what that means. Is that in Bohr's model, the proton, let me draw with a different color. So here's his proton. And he says that the electron can exist in stable orbits at discrete distances. So there's going to be an orbit that looks like this. We'll call that the n equals 1. There's going to be another orbit that looks like this, n equals 2. Another orbit that looks like this, that's n equals 3. Right? And the electron can only exist in these orbits, right? It can't exist in between them. One of the two. Okay. This is the Bohr model. It seems reasonable. Okay. And then he says that these orbits, which he calls stationary orbits, right? They're ones where the distance isn't moving, occur when the angular momentum of the electron is at integer multiples of Planck's constant, h bar. H bar has units of angular momentum, by the way. Oh, h bar's units are actually a momentum unit. So what he says is that instead of the angular momentum taking any value you want, it can only be at h, 2h bar, 3h bar, ... Okay? So what he's done is he's saying that you have fixed orbits, and the angular momentum that comes from those orbits, or rather the angular momentum associated with each of these orbits, are just integer multiples of h bar, right? Our fundamental quanta, right? So the idea is that angular momentum, just like energy in our particle in a box, is quantized, right? We can assign a number to it, and angular momentum, and it increases by h by 1 each time. Okay? So just like energy, just like energy. All right, and then he asked, and then the other thing is that they noticed that when you shine the right light at the electron, that the electron will absorb that energy and maybe emit that energy as light. These what we call transitions. So electrons gain or lose energy by absorbing or radiating energy at delta E, and that's going to be between two adjacent orbits, the energies of two adjacent orbits. So we'll call this E equals E1, E equals E2, E equals E3, and so on. Right? We don't know what they look like in terms of n, they're n squared, or how they relate to the number, but it doesn't matter. Right? He just says that when you shine a light that's resonant with the energy difference between these two states, the electron absorbs it and goes up to the higher energy state. Right? So this is just a spectroscopic transition. So at the time, let's not forget, actually, so at the time, another thing that people knew about the hydrogen atom is that when you shine light at the hydrogen atom, white light at the hydrogen atom, and you diffract that light into a prism, what you find is that the hydrogen atom, some lines or some wavelengths are absorbed by the hydrogen atom, right? There are blanks in the absorption spectrum, right? And those correspond to these differences in energy, or energies of these orbits. Right, so they understood that when you shine, right, at this point they were already doing solar spectroscopy on the sun, and they saw that the white light that came out of the sun, there were specific wavelengths that were invisible, and the assumption was that Bohr's assumption was that these absorption lines, if you will, are associated with changes in orbits of the electron around the proton. Right, it absorbs that light and gets excited. Right, which is true. Right, that's why the hydrogen atom, the spectrum of the hydrogen atom absorption atom has blank lines in it, is because there are these energy levels that the system can transition between two, just like any other system, just quantum mechanical system. All right, so those were his three assumptions. Right, all he's doing is normal old orbital mechanics, two bodies orbiting each other, but he's assuming that the energy and the angular momentum can only take quantized values. Okay, it can't exist in between. Of course, that's different than a normal atom or a normal planetary system or an orbiting system, because the angular momentum can be any value you want. But in the case of the hydrogen atom or the electron, it can only be in specific ones. Right? And so he takes this math and then tries to combine it with Kepler's laws and the laws of motion for planetary systems, orbits and stuff, and Newton's mechanics, just basic old physics. Right? So he's doing what is kind of half quantum and half classical. So he's going to say, okay, the energy is quantized like a quantum mechanical system, but the physics are classical. So let's define something. Let T be the period of the orbit. That's how long it takes to do one revolution. Okay, so that's how fast it takes to go around the circle. note that, therefore, the frequency of this orbit is proportional to 1 over t. Okay, so t is in seconds, frequency is in per second. So the frequency is 1 over t. Planck's law states that energy is equal to h nu, right? Planck's constant times frequency, which is h over the period of the motion. All right, so this is where he's applying quantum mechanics. He's assuming, again, Planck's law, right, that energy has a frequency, that it's a wave-like property. All right, but he's using very simple kind of orbital mechanics, that you're just, the electron is physically moving around the proton at some velocity, and thus has some orbit period. Right? Kepler's third law, so this is planetary mechanics. So this is planetary mechanics, or orbital mechanics. States that t is proportional to the distance between the two bodies to the 3/3 power. So I'll define this distance, for instance, as r. Sorry, the distance between the electron and the center of the proton. All right, so r here is the distance between the two bodies. So the periods of this is the rule that defines the orbits of the solar system, is that the period increases as r to the 3/2 for planets around the sun. And because this is not a gravitational system, it's an electromagnetic system, electromagnetism states that the energy of this interaction, energy, goes as 1 over r. All right, so that's just classic Coulomb's law. When you take a positive charge and a negative charge and you double its distance, its attractive force is halved. It's 1 over r. So we can combine these two facts here, right, by noticing that the energy difference between two energy levels, n-1 and n-2, is a change in time, right? You're going from a short orbital period to a long orbital period. So the change in time, or the period, is proportional to the change in energy. So when you combine these two things, what you find is that the change in energy is proportional to 1 over r to the 3/2, which is proportional to energy to the 3/2. All right, so the change in energy is proportional to the distance to the 3/2, right? That's just orbital mechanics. Just doing a little bit of unit conversion here. But angular momentum, L, is L proportional to the square root of r. So energy turns out to be proportional to, if you take to 1 over L squared. And now let's calculate the change in energy between two states, which is E n plus 1 minus E n. That's going to be the energy. So let me change that again. So from this, it ends up being 1 over L plus h bar squared. Remember, when we go up from, the angular momentum changes by one factor of h bar when we go from one level to the other. So the angular momentum changes by h bar. Energy is proportional to 1 over L squared. So the upper level energy is L plus h bar squared. Minus 1 over L squared. All right, the energies are proportional. And once you simplify this, this ends up being on the order of 2h bar over L cubed, once you kind of distribute this math out, which is proportional to minus e to the 3/2. Right? So everything works out. The change in the energy is proportional to energy to the 3/2, which is exactly what we predicted before. But when you apply angular momentum, the math works out. So the angular momentum and our energy analysis are consistent, as we expected. And now I'm going to get to the real core of his argument, and then everything kind of beautifully falls into place. But remember that he said that the angular momentum L is proportional to NH bar. Right? It depends on how many orders of angular momentum you have. And there's a factor of 2 pi that we have to add. No, there isn't. Sorry. That's H bar. I apologize. Okay. And then L is also equal to, classically, the electron mass times its velocity times its distance, which is equal to NH bar, right? Because these are equivalent to each other. So L is equal to, let me see, one sec. So what we need to do now that we know the angular momentum, we know how energy is related to angular momentum, now we have to define the velocity and the distance. And we can calculate the distance in a really simple way by considering the forces acting on the electron. The electron has an attractive force. So let me redraw this. So here's our proton, here's our electron. There's 2 forces acting on the system, because remember it's rotating. There's a force of attraction due to the fact that these are like different charges, the electrostatic charge. So we'll call that force EM, the electromagnetic attraction between the two. And as this is rotating, there's going to be the centripetal force associated with the angular momentum, or the centrifugal force, right? As you start to rotate something and spin it, it wants to stretch like this, right? So there's some centrifugal force as well. Okay, and so the electron is stable when the electromagnetic force is equal to the centrifugal force. Okay, that's what causes a stable orbit. Those are the only two forces acting on it. And so if it's in a stable orbit, those have to be equal to each other. And the centrifugal force, or centripetal force, is the mass squared, mass velocity squared over r. And the electromagnetic force is some constant, so I'm just going to write it as big K, big constant, over r squared. Okay. There's some constants in here, and I'll define them later. So it's just some constants. And so what happens then, you can solve for v here, right? The velocity is now the square root of k over mr. Right, once you do the algebra, that's what you get. Okay, so now we know everything we need to know about the angular momentum of our system. We know it's equal to some quantization, right? It's some number of units of h bar, some integral number of angular momentum units. We have mass, we have distance, and we have velocity. We just calculated velocity here. So when we plug that in here, we get equals to the mass times the square root of this constant divided by mr, r. Okay, and so what it says is that, this is interesting, what it says is that the distance that the electron is to the nucleus is quantized by this number, right? That these r's have to satisfy this number here. N has to be 1, 2, 3, or some integer. Okay, so that means that there are only allowed distances. So the allowed distances are a function of n, and they are, turns out to be, once you do the math, n squared, h bar squared, over km, and km. All right, well, these look a lot like, if you think about it, these look a lot like the particle in a box. Remember, the particle in a box energies are a function of n squared as well. And so if you calculate this, and then what you do is if you let remember that the kinetic energy of your electron is 1/2 mv squared, well, we can plug everything in and calculate energy. And the energy is minus k over 2n squared. K squared over 2n squared. And this turns out to be minus 13.6 electron volts over n squared for the hydrogen atom. All right, so I'm just evaluating the units of the constant K. So once you apply all this math, you get this nice formula that says the energy is proportional to some constant divided by n squared. And that constant is 13.6. So let's quickly calculate what that looks like. Imagine now what we want to do is we want to take the hydrogen atom and kick the electron off of it. Okay? And so that would be taking the electron from n equals 1 to n equals infinity. All right, we're going to kick it off, which means we got to excite it so far that it leaves the proton. And so E infinity minus En, or E1, well, let's calculate it. E infinity is 1 over infinity squared, so it's 0, minus 13.6 EV divided by 1 squared, which is 13.6 EV. So what Bohr predicts is that the hydrogen, all we've done, very simple, is we treated the electron and proton like a moon and a planet, except instead of gravity, they have electromagnetic attractions. And he assumed that the angular minimum of the energy has to be quantized, right? Just everything is in integer multiples. And when he gets that, he calculates that the binding energy of the electron in hydrogen, or we call this the ionization energy, is 13.6 eV. That's exactly right. This is precisely the value. So this was really, really nice for Bohr, by assuming that the electron orbits like a moon around a planet, but that the attraction is 1 over r to the 1 over r squared, like gravity is, and assume that everything was quantized, just like Planck did, he gets the right answer for the simplest question that you can ask about the hydrogen atom. What's the enthalpy change of removing an electron from hydrogen? What's the binding energy between a proton and electron? And he shows that it's 13.6 eV, exactly in agreement with theory. Not only does he do that, but he also thinks about, well, where do the absorption lines show up for hydrogen? For instance, where is E1 minus E2 minus E1? Well, this is 13 minus 13.6 over 4 minus 13.6 plus 13.6 over 2. Over 1. And so this is roughly, let's think about that, 13 divided by 12 divided by 4, so 3, so it's about 3.5. This is 13.6, so it's on the order of, I don't know what it is, it's on the order of 10 eV. And that turns out to be the correct answer. 10 eV, is that right? No, it's not, sorry. This is about minus 3.5, and then you're adding 13 to it, so it's about 8. Minus 13.5, it's 3.5 plus 8. So that's minus 5. Yeah, it's about 5 eV. And that turns out to be it's right about the right answer. I forget exactly what it is. But the cool thing is that Bohr didn't do anything fancy here. Bohr just assumed the basics, right? That things orbit like a planet do and the moon does, but that the angular minimum of the energy is quantized, right? And he gets the right answer for the hydrogen atom. Bang on. Which is really cool. And Bohr thought this was really great. Right? He ended up going ahead and winning a Nobel Prize for this and many other things. But there's a problem. He was wrong. This is in fact completely wrong, and it only works for the hydrogen atom. So this was actually kind of a disappointing thing for them. The moment that they went to helium, this broke down completely. Right? It doesn't work. And there turns out to be even more fundamental issues with it. Right? It only works for the hydrogen atom, It kind of works for lithium as well, the hydrogen-like atoms, the ones that have one electron in their valence shell. But any other atom, this theory breaks down completely. And the reason why is because what we've assumed here is a two-body system. Right? We have an electron and a proton. It's very easy to solve a two-body system, but from theory, once you get to three bodies, things become complicated. You can't solve a three-body system exactly. And so the way that you apply this theory to the helium atom is to think of the helium atom as two hydrogen atoms on top of each other. Each of the electrons interact independently of each other. It's just basically having two separate shells where each electron acts by itself independently, and you get some value for that, for the energy, and it turns out to be the worst approximation you can possibly imagine. It doesn't work at all. It's off by 3 or 4 orders, like on half an order of magnitude or something like that, factor of 3. And the reason why is because the electrons talk to each other. They have communication. But the helium atom is not just two hydrogen atoms put together, but actually it's much more complicated than that, because you have multiple electrons interacting with each other. So this theory, even though it worked great for the hydrogen atom, and it's a really nice intuitive idea, that the electron forms stable circular orbits around its proton, its nucleus, it turns out that that's not how the hydrogen atom works at all. Okay, so it turns out that that's a bad approximation. It only works for the simplest case, which is the hydrogen atom. So if that actually did work, we'd be done now. We understand the hydrogen atom. We can calculate everything we want about it. But it turns out that that doesn't work. So we got to go back to the drawing board. How much time do I got left? Okay. Got 15 minutes. Okay, so let's talk about angular momentum. Let's start all over again. All right, so let's just forget about Bohr's idea, this idea of orbits. All right, this obviously doesn't work. It only works for the simplest case. But we want to do chemistry. We don't want to just do hydrogen, right? And it gets things about the hydrogen atom wrong. And let me tell you the first interesting observation about it. We can determine this exactly. Is that the lowest state of the hydrogen atom, the ground state, is where n is equal to 1. All right, which means that the ground state of the hydrogen atom, the electron has some angular momentum to it. Right, so the L sub 1 is h bar, which means there's some angular momentum to the electron. When you go measure the angular momentum of the electron in the ground state of the hydrogen atom, which is the 1s orbital, there is no angular momentum, 0. So when we measure, so Bohr's model predicts that the psi 1 times L, psi 1, d tau, whatever that integral is, the average of the angular momentum, is h bar. That's what he predicts. But experiment shows and in fact, once we derive the theory, it'll show this either, that it's 0. The electron has no angular momentum in the ground state. In fact, what you can interpret this as is that the electron in the 1s orbital isn't moving at all. Not moving at all. At least from this perspective, right? It's not moving angularly at all. Right? And so Bohr's even at the simplest measurement of the hydrogen atom fails. Right? It's just merely coincidence that the energy stuff worked out. But this is the core of the problem, is that he doesn't even predict the right properties for angular momentum. Right? That there's some reason why, there's some fundamental difference between this orbit theory, this kind of classical theory that Bohr had, and the actual truth, which causes this difference. And this difference is very, very fundamental. Right? It's a fundamental problem with this theory. So that kind of gives us a task, is that when we put an electron around a proton, we give it no energy. It's in the lowest possible energy it can be at, in the 1s orbital, as we call it in chemistry. We should expect no angular momentum anymore. It should just be 0. Okay? We haven't. So Bohr's failed miserably, but he didn't know this. So that's not his fault. This was solved later. Okay, but that's why they went back to the drawing board, because they realized that this doesn't make any sense. Once they were able to measure these things, they said, okay, Bohr's model doesn't work at all. Let's go back and think about it again. How much time we got? 15 minutes. Okay. So the way I want to tackle angular minimum is not from the perspective of the electron and the proton. Of course, that's what we want to deal with. But it's actually easier to think about it from the perspective of a molecule. We'll actually build up the tools of angular minimum using molecules, and then we'll apply those tools to the hydrogen atom. They'll become very useful. It's just much easier to think about a molecule rotating and thinking about the physics of that, and then applying it to an electron around a proton. Right? And it turns out this is kind of the way that we typically learn it, and it works really well. So what I want to do in the last 10 minutes is just introduce our problem. So what I'm going to do is we're going to start with a very simple molecule. Maybe HCl. All right, so I'm going to put an H here and a Cl here. All right, and I'm going to define a few things. First, let's define the center of mass of the system. Of course, when you have a two-body system, think about these as two heavy balls. It has a mass MCl and a mass of hydrogen. Right, two balls on an infinitely thin string, has no mass. We can define a center of mass here. We'll talk about the math of that next class. All right, and what I'm going to do is define a couple distances. I'm going to define the distance between the Cl and the center of mass as, let's see which one I do. Oh, we'll just call it R1. Okay, and then I'm going to define the distance from the hydrogen atom to the center of mass as R2. And then the whole distance between the hydrogen atom and the chlorine is R. So R equals R1 plus R2. Okay. And what we're going to do is we're going to spin this. So let me draw, again, this is all in a plane. So let's see if I can draw this in a plane. Draw a parallelogram. So there's our plane. And we can think about the rotation of our two masses around the center of mass. So we have a rotation that looks like this for Cl. Right, this is the center of that orbit. It doesn't really look like the center. I'm sorry, let me change that. Right, so this is the center of our orbit, and it's around this. So maybe more like that. And then we can also define the orbit of the hydrogen atom around the center of mass as well with a circle. So it's like from here to here. Something like that. Okay, and we're gonna spin the system around this axis. And so imagine there's an axis coming out of the board like this, and the molecule is going to rotate in the plane of the board like that. We're going to rotate the two atoms together, attached with this barbell, in the plane of the board. Okay, remember that the angular momentum is equal to R cross P, where this is the momentum in the distance. So the angular minimum of the system is the distance, this R here across the momentum of the system. All right, and the thing about when you do a cross product, so imagine that, let me try to draw this in the plane of the board. It's just a little bit of vector calculus. So if your R is in this direction and P is in this direction, then L is in the perpendicular direction. So L is normal to the plane of the rotation, so the molecule's angular minimum is pointing out of the board here. And we use the right-hand rule, which means that the right-hand rule, you curl your hand in like this. Maybe you guys remember this from physics. And this tells you if the angular minimum is in this direction, it tells you which way the molecule is rotating. So if our molecule is rotating this way, the angular minimum is pointing out of the board towards you guys, and that means the molecule is rotating counterclockwise. So L out of board, CCW rotation, L inboard. CW rotation. Right? So that's the right-hand rule. I just want to get a sense of what the physics are going. We're just making these atoms orbit their center of mass by applying a little momentum in the direction of the board at fixed distance from the center, and you get angular momentum out this way. Okay. And so the interesting thing about angular momentum is that we can relate it to momentum a little bit. So the momentum of a particle is P equals m times v, where this mass of the velocity of our system. And angular momentum has a very similar form. What we call it is L. And instead of mass, we use a different number called I, which is called the moment of inertia, or a rotational mass, times a velocity. And the velocity we're going to use is the angular frequency. And I'll explain what that is. Imagine we're on this board. Imagine this molecule is rotating, okay, and ask the question, how long does it take for it to complete a 360-degree rotation? So let's say that the frequency of rotation is nu, right? That's what we use for frequency. And this is time to rotate 2 pi radians. Right? We think of it drawing a circle, and to draw the whole 2 pi of a circle, it takes nu. And so the angular frequency is the frequency per radian. So this is the speed of rotation per radian of a circle. Okay, so it's some velocity, if you will. Right? So our equivalent of velocity is how fast the system is rotating, how fast can it subtend a circle in a given amount of time. Right? How many radians in 1 second, if you will. So it's exactly the same idea here, except here we have a inertial mass, or a weight, and here we have a linear velocity, right? Motion in x, y, z. So it's the exact same idea. Right? Momentum is a linear momentum in a certain direction. Angular momentum is the same concept. We have a mass associated with rotation and a velocity associated with it as well. Okay. So even though we're dealing with a molecule, we can use this stuff for a proton and electron. The only difference between an HCl and a proton and electron in terms of its rotation is that in the proton's much heavier than the electron. So in a proton-electron system, here's that barbell between them. We're rotating the electron this way with some angular momentum L equals I omega. Is at the center of mass, which I'll draw in blue, because the proton is about 1 AMU, and this is on the order of 10 to the minus 4 AMU. The center of mass is basically in the proton. Okay, so it's the exact same problem, except now that the axis of rotation is in the center of the particle. That's what we assume. We assume that in the hydrogen atom, the proton is so much bigger than the electron that the center of mass is right in the center. Right? And so the physics that we come for our molecule rotating are the exact same as the electron and the proton. We've just shifted the center of mass slightly. So the physics look a little different on the board, but the dynamics, the motion looks different. The proton stays still and the electron's rotating around it, but that's no different than having 2 masses of similar size rotating around the center of mass. It's the equivalent problem. All right, so everything that we come up with angular momentum, we can directly apply to our hydrogen atom, right? All the physics, right? So we can start with a simple problem that we can understand conceptually, rotating a physical object in space, and then apply it to a more abstract concept of an electron moving around a proton. And of course, it's even weirder for an electron and a proton because the electron has no size. Electron's a point. Drawing it like a sphere, a circle like this is actually not a good idea because in fact the electron's just a point. There's no physical size. And of course the proton has a size, but the electron does not. So that's quite a bit different than this, right? Where these atoms have very obvious physical sizes like particles. But here they don't at all. But thankfully the physics works out the same no matter what, so we don't have to worry about it too much. What that effectively means is that the moment of inertia becomes very small because there's not a lot of mass moving around. Okay, so we have all of this math, right? So we have angular momentum, right? And it's this moment of inertia times the angular frequency, our mass times our velocity. Okay, except we're doing it in a circle instead of in a line, right? Instead of moving something along the line, we're moving it in a circle. And we're not quite, we only have a minute left, so I just want to write one more thing down. This is another thing from physics, is that the kinetic energy of our barbell, or our molecule, rotating, which we call T, right, T and V, is equal to L squared over 2I. Okay? So, and again, this is very similar to normal momentum, linear momentum. Kinetic energy is P squared over 2m. Right? It's the exact same equation, we've just replaced some values. So instead of linear momentum and an inertial mass, the rest mass of our molecule or particle moving in space, we have some angular mass that we'll have to define, which we will next class. And we also have this new angular momentum, which works just like momentum, but it's in a circle instead of in a line. Okay? So the math of angular momentum and the math of regular momentum are very similar. They just are, one's in a circle and one's on a straight line. It's the only difference between the two. And we're going to be able to use the power of a circle, the symmetry of a circle, to come up with some really neat things about angular momentum. There's some special limitations. Key differences between these two ideas, angular momentum and momentum, because this is on a circle. Circles have special symmetries. And that will cause very interesting effects in angular momentum that you don't see in other types of momentum because of the circle. The circle is everything. The circle is God. And as we'll find, that the fact that we're dealing things on a sphere or on a circle in a hydrogen atom will play a big role in understanding the structure, this idea of spinning something around a circle. Okay, I just want to stop there for now. I've just kind of thrown some basic math at you. We'll come back to this next class. What we'll do is we'll quantize the rotation of this molecule. All right, we'll come up with we'll solve the Schrodinger equation for it just like we did the particle in the box. We'll get wave functions, we'll get energies. We'll be able to do spectroscopy on it, and we'll be able to determine the structure of the molecule from the angular momentum that we observed as well. All right, so we'll talk a little bit about that. That should just take the next class, and then we'll take this information and then connect it to the hydrogen atom after that. Okay, have a lovely weekend, everybody. Let me know if you guys have any questions about the homework. I'll see some of you soon.
We're going Dr. Smith.
Hey, you too, thank you. Have a good one. You too.
Thank you.